Hello everyone, today we're looking at dilations, which is another kind of transformation, and we're going to be talking about scale factors. We're going to be talking about how we draw a dilation. We're going to be looking at the properties of dilations, and all of this is going to come back again in a future unit when we're studying similarity. Here this is just put into our unit on transformations, as it is a kind of transformation, but we'll deal more with it in a future unit with similarity. So let's talk about what we see here in the box to describe a dilation. So a dilation is also a kind of transformation, but this is the first time that we have seen a non-rigid transformation. A rigid transformation keeps it the same size and shape. Now it will not be the same size or shape. We'll see in a moment. And so we have looked so far at translations, where we move an object up, down, right, or left. That was rigid. We've looked at reflections. That was rigid. We looked at rotations. That was rigid. All of those shapes created an image that was the same size and shape. Now we have one that will not be the same size or shape. We'll figure out which one it is. So it is a non-rigid transformation that maps, or you should say sort of lines up or matches up points to other points in the coordinate plane. A rule in this notation for a dilation centered at the origin is, so here's our rule. We had lots of rules for reflections and rotations. This time our rule is multiplying a scale factor to the x-coordinate and a scale factor to the y-coordinate. So what we are using as k is the multiplier. So if it's 2 times bigger, if it's 3 times bigger, that would be the scale factor, and that's what we would then multiply to the x and y coordinate to get the new location. So that's this scale factor. The scale factor is the ratio of the length of an image segment to its corresponding pre-image segment, and that is the scale factor called k. The scale factor k of the dilation is its ratio. So let's set this up. Remember, a ratio can be represented as a fraction. What is our fraction? It is a comparison of lengths. Lengths of what? Lengths of the image to its pre-image. So here's our fraction. We said it's a ratio of lengths. The lengths of the image to its pre-image. Alright, so it looks like a formula, but really that's just putting in notation what the description was telling us, that it is a ratio. There's our ratio of lengths of image to pre-image. So it has to be the corresponding sides to calculate that. We'll do that on the next page in just a moment. First, let's draw our very own dilation. Here's our pre-image triangle ABC, and we want to dilate triangle ABC by a scale factor of 3. And oftentimes these are from the origin, but they don't always have to be. Here it specifically says from the origin. So, setting up a little bit of a table here, we want to find what our original coordinate points are, so that we can then change them according to our rule for dilations. So, there we go, that's better. Point A is located at 1, 2, 1, 2, 3, so that's 2, 3. Point B is located at 1, 1, 2, 3, 4, 5. C is located at 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, 5, 4. So because we have a scale factor of 3, then what we're going to do is we're going to multiply our scale factor to all the coordinates. That's what our rule was saying. Take that scale factor and simply multiply it to the x and multiply it to the y coordinate. So what that means then is that A prime has coordinates that are, so 2 times 3 is 6, 3 times 3 is 9. B prime has coordinates that are 1 times 3 is 3, and 5 times 3 is 15. And for C prime, 5 times 3 is 15. 4 times 3 is 12. There it is. So let's plot those points. A prime is at 6, 9. B prime is at 3, 15. And C prime is at 15, 12. If you compare the pre-image with the image, you can see that it is the same shape. It is still a triangle, but it's obviously much bigger. 3 times bigger, right? So that's why we call this a non-rigid transformation. It is a transformation, but it's non-rigid. That means it's changed in some way, and it's the size that has changed. Now here's a way to check to see if your points ended up in the same spot, and it's also going to be a property of dilations. Let's draw a construction line through corresponding points, and we'll extend it all the way through the center of dilation, which for us was the origin. So if you do that, what you should discover is that all 3 of these points are collinear. Collinear means they are together on the same line. So there's my construction line. There's A prime, there's A, and there's my center of dilation. All 3 are collinear. That's how I know I have A prime in the right spot. That should be true for the B's. So here's B prime and B. They should be collinear with the center of dilation, and they are. It should also be true for the C's. So let's line up C with C prime, draw that construction line, and that's a set of collinear points. What you also see is kind of this funneling effect, and now it looks like a 3-dimensional object if you look at the big triangle and the small triangle as if they were all on one prism. In art class you learn about one-point perspective, and that's essentially what we have here. A dilation with one point of dilation here creates this one-point perspective type of object, but that's how you can check your work. So we have these properties of dilations. Again, we'll talk more about them in a future unit, but here they are. If you take a look at these corresponding sides, so that means we're looking at matching sides. We're looking at sides, for example, from A to C and A prime to C prime. Those are corresponding sides. Or B to A, or B prime to A prime, those are corresponding sides. So what we see is that these corresponding sides are proportional. Let's talk about that. We haven't proved it, but proportional means that they would be scaled up by the same scale factor. So if we actually measured this length and its corresponding side, we would find this length to be 3 times bigger. That's what we mean by proportional. If we measured the length from A to B, then the length from A prime to B prime will also be 3 times bigger, because that's the scale factor, because they are proportional. That's what we mean by proportional. Each pair of corresponding sides will create the same scale factor. Also, corresponding angles are congruent. We haven't talked about the angles. We've been focusing on the sides and the vertices. So let's take a look at one of the angles. Let's look at the angle at point A. And I'm just using tracing paper to kind of outline this. If you take a look at angle A, that's the angle we're talking about. Even though the sides are very small, we want to look at the space between the sides. And if we compare that with the angle at A prime, notice that the sides line up, meaning there's the same amount of space inside. That means this angle at A and A prime have the same size, the same measure. They are congruent. Those are the two main properties. There's some other features as well, but those are the big ones, and that's what I want you to learn. So let's turn the page and go over to this next example where we're going to draw our dilation and take a look at these two properties, or a couple of properties here. So let's draw a dilation of triangle ABC with vertices of, there they are. Let's use a scale factor of 1/2 and using the origin as a center of dilation. So step 1, draw the preimage. A is located at 2, 0. B is located at 6, -4. And C is at 8, 2. There's our preimage. They tell us to use the scale factor of 1/2, and so if we're thinking about it in terms of writing the rule, we'll take each coordinate point, we'll change it in this way, and with the dilation it's a multiplier. So we will go 1/2 times x and 1/2 times y. 1/2 times x is the same thing as x divided by 2, so you can think of it that way as well. So here we're setting up our table for the a prime, b prime, c prime. Let's multiply 1/2 times each coordinate. So here a is at 2, 0, so 1/2 times 2 is 1. 1/2 times 0 is 0. On point B we have an x coordinate of 6, so 1/2 times 6 is 3. And 1/2 times -4 is -2. And on point C we have 8, 2. So 1/2 times 8 is 4, and 1/2 times 2 is 1. So let's plot these points. A prime is at 1, 0. B prime is at 3, -2. And C prime is at 4, 1. So it should look the same shape. It is still a triangle. The triangle hasn't been distorted. It's still the same shape of a triangle, but it is definitely smaller in size. So we talked about this first property being that the corresponding sides are proportional. We're not going to check every pair of sides. Let's just focus on one pair of corresponding sides. So we're looking at this length from C to B, and this length from C prime to B prime. So those are the corresponding sides we're focusing on, and because they are slanted in length, we have to use the distance formula. We can't just count the length. And so we'll set this up. Here's the length from C to B. Let's use our distance formula. And the coordinates are right up here. Here's the coordinates of point C and point B. Alright, so take those x coordinates and subtract them. So 8 minus 6, quantity squared, plus sign. Take those y coordinates and subtract them. So we have 2 minus the -4, square that results. And again, all of that is under the radical. So let's focus on what's inside those parentheses. 8 minus 6 is 2. And 2 minus the -4, that turns into adding a positive, so that becomes 6. We'll square each of those, so under the radical we now have 4 and 36, which gives us square root of 40. Now you remember how we reduced our radicals. We don't want to go to a decimal. That won't help us out any. We want to find factors that are perfect squares. So let's take that 40 and factor it into 4 times 10. So we will have a final length in simplified radical form of 2 times the square root of 10. We want to compare that with C prime, B prime. Alright, so those coordinates are right here. So let's set up our problem. Take the square root of, subtract those x coordinates of 4 and 3. So 4 minus 3, quantity squared, plus the y coordinates are 1 and -2. So 1 minus -2, quantity squared. And again, that subtracting a negative turns into adding a positive. So we end up with, under the radical, 4 minus 3, which is 1, and we'll square that in a moment. Here we have 1 plus a positive 2, which gives us 3, and we'll square that on the next line as well. So that means we have 1 plus 9 under the radical, which gives us root 10. Its factors are 2 times 5. Neither are perfect squares. That does not simplify any further. Now we want to compare the lengths, so we can look at them, but let's compare them by actually calculating the scale factor. Remember, we said that we can calculate the scale factor with this ratio. We'll take the corresponding lengths of the image over the pre-image. That's what we're going to do right here. So let's compare them, and essentially what we're doing is we're finding the scale factor. So we said to do that we want this ratio of the image over the pre-image. Alright, so which one is my image? That's the one with the prime notation. So there's the prime notation. That's the length of root 10. Which one is my image? That was the original without the prime notation. That was the 2 root 10. Now, we want to reduce the fraction if at all possible. And you notice, hey, look at those root 10s. They can cancel out. That's great. But be careful. The answer here is not just 2, because we have to have a fraction here. Don't forget there is this invisible 1 in front of this root 10. So when the root 10s cancel out, you are left with 1/2. And that confirms that we did our work correctly, because that matches the scale factor that they told us. We knew it was 1/2, so we already knew the answer we should have gotten when we reduced the radical. Here's another example using a scale factor. Here in example 4. You are making your own photo magnets. Your photo is 8 by 10 inches, and the image on the magnet is 2.8 inches by 3.5. What is the scale factor of the reduction? So let's draw an image, let's draw a picture. This is the pre-image of the photo, which is the 8 by 10. So this is the pre-image. And we are reducing it down to this little magnet that will end up being 2.8 inches and 3.5 inches. So again, you want to line up the corresponding sides, meaning the largest dimension of 10 inches on the original I happen to put on the height, so that means the largest dimension on the magnet should also be on the height. So these are the corresponding sides. The smaller dimension I happen to put on the bottom. So again, you want the smaller on the bottom for the magnet as well. This then is our magnet, this is the image. So, what is the scale factor? We use that ratio of image over pre-image. And again, we want corresponding sides. Well, we have lots of numbers here, so we can either pick corresponding heights or corresponding bases. It doesn't matter. We could do either one. And so let's take one of them. I'll do the base to the base. So here's the image base of 2.8 inches, and here's the base dimension on the pre-image of 8 inches. Now, I don't know if you are seeing what I'm seeing here. This is not our final answer, right? We cannot let decimals exist inside fractions. That's very bad form. We never do that. An answer is either in fraction form or it's in decimal form. We can't mix like this. We can't mix decimals inside fractions. So that's bad. We want to convert it, and that means we'll just use our calculator and do that division. So you grab your calculator and just go 2.8 divided by 8, and the number that you get is just in decimal form, and that's our scale factor. So when we shrink the photo down to the magnet size, our scale factor is 0.35. So notice it's less than 1, which means it is in fact shrinking. That's what we saw in the previous example. Our scale factor was 1/2. That's less than 1, so it was shrinking. Whereas on the first page, our scale factor was 3. Bigger than 1, so it got 3 times bigger. Now, what we've been doing so far when we've been graphing these has been working with a center of dilation that has been at the origin. But it doesn't have to be, and we're going to see that represented here in these last two examples, examples 5 and 6. Example 5, there is no coordinate grid, but the idea is that we have some center of dilation that is not at the origin. We don't know where it is, but it's not at the origin. And when we get down to example 6, we'll see that this center of dilation also is not at the origin. We'll show you how to find that. So here we have two objects. We're calling this object A and object B. By the names themselves, we don't know which is the image or the preimage. So take a look at these corresponding points. On triangle A, we have this point called point P, and on triangle B, we have a corresponding point called P prime. There's the prime notation, so that's how I know this triangle B is the image, and triangle A is the preimage. So if you compare the preimage to the image, you can see it got bigger. So our scale factor is definitely bigger than 1. What we want to do is find the scale factor, and we'll also find the value of x. So look at these construction lines. Remember, we said that the construction lines create these collinear points, where these corresponding points all line up with the center of dilation. Point C is our center of dilation. Here we have another construction line, and we have these corresponding points. And here's another construction line saying that the total distance is 14 from that center of dilation to point P prime. Here we have a little segment of length 4, and here we have a little segment of length x, and this is the total length of 14. This is our segment addition postulate. Going way back to Unit 1, we learned that you can have two segments right next to each other and add them up and get the total of 14. So let's work backwards to subtract. 14 minus 4 would mean x has to be 10. Right? 10 plus 4 is 14. So that's our segment addition postulate. So we found the value of x pretty easily. To find the scale factor, again, we want this ratio of image to preimage. But one thing is a little bit different here. When we were looking at this ratio of image to preimage, we were always comparing corresponding lengths. Like the photo to the magnet, we compared the base to the base. Or we could have compared the height to the height. And now in our current example 5, I would love to compare the base to the base. But we don't have numbers there. We don't have any lengths on the sides of the triangles. That's okay, as long as we compare any kind of distance, even if it's on a construction line. So we want to take a look at the length, or the distance, from the center of dilation to those corresponding points. So we want this length. This length from point C to triangle A goes to the preimage, and that's the length of 10. We don't want the length of 4, because that doesn't go to the center of dilation. We want this length that goes from the center of dilation to triangle B. So those are the two lengths we want. We want the image, which has a length of 14 from the center of dilation, and we want the 10, which is the length of triangle A to the center of dilation. That's our ratio. That turns into 1.4. That is our scale factor, and we said it should be bigger than 1 because we saw that the image was bigger than the preimage. So this is to illustrate that the center of dilation doesn't have to be at the origin, and secondly, that we can use any pair of corresponding distances, even distances that are from the center of dilation, not just distances on the figures themselves. Alright, let's take a look at our final example. Here we have not a triangle, but just a segment. We're keeping it really small this time. A dilation maps point A to A prime and point B to B prime. That means A and B form a segment. That's your preimage. A prime, B prime form the image. And again, it's just a segment. So let's first draw the preimage. A is at 3, 4. And B is at 2, 2. So we're just using a segment here, not even an entire triangle. That's the preimage. Let's go ahead and draw the image. So A prime is at 6, 4. b prime is at 4, 0. So if you look at the length of AB and the length of A prime B prime, you can see that A prime B prime is definitely bigger, so we would expect the scale factor to be bigger than 1. Okay, now when we find the scale factor, we want to use this ratio. That means we want to compare lengths, but the length is a slanted line, so we could use our distance formula and compare the lengths. But we could also compare the length from a corresponding point to the center of dilation. So we actually have two different ways of doing this, but where is that center of dilation? So I'm going to find that first. I'm using part B here to find the center of dilation. How do we do that? Well, remember, we can draw these construction lines, and they will line up with those corresponding points, and they'll all funnel down and pass through a common point we call the center of dilation. So let's see where that is. I'll use my straight edge here, line up A with A prime, and then I'll line up B with B prime, and so just visually look to see where those construction lines meet. There it is. There's your center of dilation. So notice it is not at the origin. And we can see it is located at 0, 1, 2, 3, 4. So we actually answered part B first by creating those construction lines. Now, notice that this construction line is horizontal. That means we could just count the distances. So, to find the scale factor, we want to find corresponding lengths. We have a couple choices. The first choice is to use the distance formula to calculate the length of these slanted lines, and that would be very similar to what we did up here in example 3, where we used the distance formula to calculate the length of those slanted lines. We could certainly do that. Option 2 is we can use the distances of the construction lines themselves. Well, if we use this construction line, that would be slanted, so that's still distance formula. But if we use this horizontal construction lines, we can just count, and that'll actually go a lot faster. So let's count the distance now from the center of dilation to point A. So that distance is 1, 2, 3. And then let's count the distance from that center of dilation to point A prime. That distance is 1, 2, 3, 4, 5, 6. See how much faster that is. So to find our scale factor, we want this ratio of image to pre-image. And the image is the one that goes to the A prime, so that's the 6. 6 is in the numerator. The pre-image is the A without the prime, that's the length of 3. Our scale factor is 2.